how you doing?
Trying to share my. Okay. Good.
Excellent. That looks great.
Okay. Thank you very much. And hello, everyone. It's nice to meet you here. And I saw some old friends. And because of COVID, some of you we do not see each other over a long time. All right. So I'm.
Oh, sorry, Haitang. Maybe we'll wait a few minutes. I think we have you scheduled later, just in case people are planning to come in at the start of your talk. So how's the summer been for you? Have you been busy with research? How's the summer been for you? Has it been busy?
Kind of, but not that much.
Yeah. I've heard it's always a good opportunity to, when the teaching stops, to do a lot more research work.
Right. But I think the situation here is not so bad. Because I mean, it has been controlled very well. So it's nice. So you stay home and try to get a mask. Quite safe.
Yeah, definitely.
Are you now in Chengdu or in Hainan?
No, I'm in Beijing right now. I came to Beijing last month.
I see.
And I almost stay home.
Maybe you can't leave Beijing since some victims attacked in Beijing.
All right.
Always like it.
We are not encouraged to go outside.
Okay, Haitang, maybe we can probably get started soon if you fancy.
All right. So, okay, it's my pleasure to present our current work to you. And thanks for Yang Hui for the invitation, and thanks for Ivy. My talk is hyperbolic string vertices, and it's basically we claim it's building blocks of space-time. All right, this is outlines, and we have two preliminaries to introduce first. And the fourth part, relation between the string vertices and reflected surfaces, is the main body of my talk. This work has not appeared online, and hopefully I think we can finish it in a couple of days and upload to archive. This work is collaborated with Professor Peng Wang and Hou Wenwu. The motivation of our work is that we try to propose a relation between canonical periodicism of multi-partite mixed state of safety 2 and the hyperbolic string vertices of closed string field theory. Therefore, just from this sentence, we can say that there are two subjects. One is closed string field theory. I think there might be not many people are familiar with this subject. Another one is a very popular one in recent years. It's about the entanglement entropy. Because we are talking about the relationship between them, I have to first give some introduction of those two subjects for who are not very familiar with those subjects. All right. The first one, so the first part is I give some brief introduction of hyperbolic string vertices in closed string field theory. Closed string field theory, probably most of you are not very familiar with this, so I'm going to skip the details and just introduce what we need here. In CSFP, what's important is the string vertices of shear amplitudes are defined by the set of string vertices, just like this here, with latitude Euler numbers. This condition is very important. We are going to say those vertices are subsets of modular spaces of compact Riemann surfaces of genus G and unmarked points, with choice of local coordinates defined at those points. In order to get a consistent quantum theory, those string vertices must satisfy the BV equation. The BV equation originally is an algebraic equation. However, because we are talking about string vertices, which is a geometric object, the algebraic equation, the BV equation, can be translated into the geometric master equation. The form is identical, but we are going to say that it has a geometric interpretation. The vertices is right in this form. It's a summation of different genres and different punctures. For those part, this part is just to satisfy this condition. We can say that this one simply means that the Euler number is negative. So it's inspiring, it's speculative to think probably we should endorse some like hyperbolic metric on the surface. It turns out that's very crucial. Let's make some explanation of the notations. The partial denotes to take boundary of a surface, because this we are talking about the geometric objects, so therefore it's surfaces. And the delta just means to remove the coordinate disks of two marked points on a Riemann surface and then twist showing the boundaries of the disk. And the bracket acts on two vertices to just remove one disk in each of them. And then twist throwing the two disks together. So it's quite easy to see this from here. However, to make the string vortices to be valid, to be a consistent quantum theory, there are two conditions must be respected. The first one is that we have to first prove the string vortices exists on the modular spaces of Riemann surfaces. This is highly non-trivial. And then, of course, another very non-trivial condition is to prove that the string vortices satisfy the BV equation. Just this equation, all right? This is the BV equation. Oh, by the way, sir, I forgot to say the H bar is a Planck constant. So for the classic, this equation is intrinsically quantum. For classical one, we just take H bar to be 0. For H bar to be 0, this term disappears. Only this term and this term, the first and the third terms are left. And here, the summation only left with G equals 0, 1. That's a classical version. For quantum version, we just have this. We need to prove this. Previously, there had been two proposals to solve this problem. The oldest one and the most popular one was the minimal error metrical approach. It has a long history. However, with this approach, the requirement 2 can be easily satisfied, but the requirement 1 is difficult to prove it. Just a few years ago, 4 years ago, almost, Musavin and Pias proposed a semi-hyperbolic string vortices method. In this method, they can easily, not easily, sorry. It's not hard to prove the existence of string vortices on the modular spaces. However, to prove this one is very, very hard, and they can only do this percutatively. At the first order, they had it done, but there are corrections in higher orders, which is looks very hard. Just 2 years ago, Castello and Suiva made a very simple but brilliant improvement on the MP approach, namely replacing. In MP approach, they endow a hyperbolic metric on the Riemann surface, but the boundary is not geodesic. It is a horocycle. It turns out when we replace the horocycle by the geodesic with this net condition, the length must be constrained, restricted. Then those two conditions can be satisfied perfectly. There is another condition: the system of the vortices are not less than L. I didn't write down the explanation. We can simply understand it this way. This means that what a closed geodesic, what a simple closed geodesics, the length of the simple closed geodesics are larger than L. L is the boundary geodesic. So basically, it's larger than the boundary geodesic. This is what they done 2 years ago. And their construction has 3 steps, so we just introduce one by one. The first step is to construct the right-angled hexagon with side length. Here, the length of, let me see, sorry. Oh, okay, this is 1/2 L, and with this length theta. The red lines are geodesic curves. We require gamma A equals gamma B equals gamma C. And actually, in fact, we have, if we look at the boundary, this is a Poincare disk. first, this is a Poincare disk. Poincare disk we split into 6 parts. But A equals B equals C, and of course, a small a equals small b equals small c. In this case, and this is the geodesic curve to connect, bounded by the boundary of C, and these are the same. And there is the theorem, the ultra parallel theorem in parabolic geometry, which means that in the Poincare disk, any parallel for ultra parallel geodesic is embarked by the unique perpendicular line, which is this one. In addition, this perpendicular line is the shortest path between the parallel for ultra parallel geodesics. Here we just draw it's not a straight line. We just in order to be convenient to have it to draw it, we write down in this form. All right, this so prepare this one. The final one is like this. Okay, it's one of the red line and the blue line are geodesics. This is step 1. And step 2, we glue in 2 identical copies of the hexagon along the edges gamma I to obtain y points, which possesses 3 geodesic boundaries with equal length. This one. So this is the original one, and we prepare on that identical copy and glue the red geodesic together to form the y pan. For those of you who are familiar with the hyperbolic geometry, I think this is quite simple. This is called y pan in hyperbolic geometry. This y pan is denoted as v tilde. This because it has no genus, so 0, and 3 punctures. We say 3 here. It's almost done here, but there's just 1 step left. The third step is just graft some semi-infinite cylinders of circumference L to the geodesic boundary like this to obtain a complete spin vertices of V03. Because the semi-infinite cylinder can be conformally mapped to the marked points, conformally mapped to the ground. We got local coordinates around the puncture. Moreover, the cylinders can be understood as Feynman propagators, which are used to connect different string vertices. And of course, we can construct higher order string vertices VGN with these y points. This is just some routine construction in hyperbolic geometry. And finally, graph semi-infinite cylinders on the punctures. One got VGN. All right. This one, well, we have 1 step left to finally solve the BV equation. It turns out to solve the quantum BV master equation, L must satisfy some constraint. For classic one, there is no constraint on L, but for quantum one, we have to restrict L to have some specific range. In order to do this, there is a very important theorem in hyperbolic geometry, which is called corner theorem. For the corner theorem, let's sigma a simple closed geodesics on hyperbolic surface S. The corner is defined in this way, which means that the distance of the points to the boundary is not larger than 1/2 omega I. This is what we call omega I with the width, and we require this condition is satisfied, the omega I and the length of the geodesic boundary geodesic. Color theorem says, all right, those just look at this diagram. Those 3 guys, they are disjoint. They do not touch each other. Once this one is satisfied, this is the famous color theorem in hyperbolic geometry, and we are going to use it. This is crucial. A critical L star then is defined as this, because omega star equals L star, we got that this one equals 1. Therefore, they just equals to two arcsinch 1. This is the number. And the Castro and the Slayback proved is L in this region, the vertices do solve Biot equation precisely. So we go to the next subject, the ingredient. We now turn to another ingredient of our work, the bipartite reflecting entropy. The reflecting entropy is based on canonical purification for a mixed bipartite state that will be in HAB. I think some of you in the room are familiar with this. That's once fixed on a property of orthogonal basis, the purification doubles the Hilbert space. This is okay. This is the psi I. No, I cannot say psi. This represents a mixed state. This is the density matrix of the mixed state. We can only do it in this way, and the purification leads to a pure state based on this. Density matrix, we got this. This is a pure state. This process is called purification, and with this pure state, we can of course recover this one by tracing out the star part. However, we are going to another way. We first define the density matrix of AA star. AA star is got by tracing out BB star part. Right, this is the pure state. This pure state, and we trace out BB star, we get a AA star. Then the reflecting entropy is defined as the von Neumann entropy of this mixed state. But here we are, what we are concerned with is the Bark dual of the reflecting entropy. The previous one, this is the conformal field theory. Basically, theoretically, this could be calculated in conformal field theory, although for most of the cases, it's not an easy job. What we are concerned is the Bark part. The Bark part is the Bark dual of the reflecting entropy like this. Just look at this diagram. We have the original A, B, C, C bar, or C, C prime. This is the original mixed state. The purification process is basically prepare an identical copy of the original surface and glue the geodesic gamma C prime respectively. All right, the red curve is always a geodesic. We glue them together. This is the purification process. We got this one. This one, before this green curve is called the entanglement wedge cross section (EW). This was conjectured to correspond to the purification entanglement entropy. Okay, let me just do not talk too much about that. Okay, the green line in the bark is called the entanglement wedge cross section EW, which is defined as the shortest line, which is also, of course, geodesic connecting boundary anchored on geodesic gamma C and gamma C prime. This one, the EWCS. The bark dual of canonical purification is gluing CPT copy of this these two copies along gamma C and gamma C prime. Therefore, in the right hand side, the green curve is the bark dual of SR. Okay, this is reflected entropy. The dual of the reflected entropy will this curve is called the reflected minimal surface actually. This curve, because it's in the bark, it's a bark dual of the reflected entropy. without confusing, sometimes we also simply call it as reflective entropy. The precise name of this curve is reflective surface. We can easily say that SR equals to EW here. This process can be easily generalized to multi-part mixed state. Because I cannot spend too much time on this one, so it's let's just do it briefly. It is worth noting that the reflective entropy SR or EWCS does not always exist. Just look at this two diagram. This two diagram I copied from other places. There is a phase transition point between the connected and disconnected entanglement wedges. When part A and part B are distant, they are far. If they are far away, then the RT surface is this one and this one. We can say they are just disconnected here. In this case, there is no reflective entropy, so this one equals 0. If they are close enough, in this case, the RT surface is replaced by this geodesic curve, which connects part A and part B. In this case, we got SR and EW. Therefore, from this two diagram, we say there are minimum value of SR or EW, which turns out the minimum value is this one. All right, but in safety, this they cannot. We do not say the precise minimum value of this one. What we only know is that must be larger than this one, 2L star. Which means that when the length of SR approaches to this value, the entanglement wedge, which is enclosed, this entanglement wedge disappears. To figure out the relation to string vertices, we need to consider a canonical purification of tripartite mixed state. Previous one is bipartite. And here is a tripartite mixed state, which is gluing two copies of tripartite entanglement wedge along 3 red geodesics in the back. We can see from the diagram, which is straightforward, we have three part A, B, C, separated by small ABC, and this is the red one, geodesic one anchored on the boundary, and the green the green curves are also geodesics. From theorem 1, we know that it's unique. There is only one geodesic, which is perpendicular to 2 geodesics. And we glue them along the red curves. Finally, we got the y pants here. And with the length of the green simple geodesic, which is called, of course, this is the reflective surface. This this reflective surface just represents the entanglement entropy of A star, A to the rest part here. So we write it in this form, SRA double dots to BC. This is just some definition in the entanglement entropy. All right, this we are. I think I finished the preliminary part. From the preliminaries, we see that there are apparent similarities between the spin vertices and reflective surfaces, because we saw y pants in both cases, and the geodesic boundaries in both cases. From theorem 1, the outer parallel theorem we introduced before, there is only one perpendicular geodesic between 2 geodesics in the Poincare disk. Therefore, we have the corollary one. The geodesic boundaries of string vertices and reflective surfaces of canonical purification are same type geodesics in hyperbolic geometry. Now we need the theorem 2, which is in Busser's book, the theorem 3.1.7, which says that given 3 simple closed geodesics with length L, A, B, C, of course larger than 0, there exists a unique hyperbolic y-pants with 3 alternative sets of length L, A, B, C. This theorem tells us that the boundaries length L of string vertices V03 or bipartite reflected entropy SR of tripartite canonical case uniquely determine a y-pants in the bark. It is hence possible to obtain relation between string vertices of V03 and entanglement canonical purification of tripartite mixed state. Moreover, since every compact Riemann surfaces can be built by y-pants, what we want to show is that the bark interpretation of any multipartite canonical purification can be built by the string vertices. This is what we want to do. All right, here, because to this end, let us record the constraints of L and SR in 2 theories, which are given in the following picture. Here, this one is the string vertices. The string vertices is bounded by 3 geodesics. The length of the geodesics are equal. One of them is just L. On the other hand, this one is the tripartite reflected surface. This is reflected surface. Here is A. This represents the reflected entropy between A and the rest part of BC. And here, of course, C to AB, B to AC. Right? For this one, there is no requirements, so it's totally arbitrary. The only requirement is that SR must be larger than 2L star. We just said that SR has a minimum value. However, for this one, the story is a little bit subtle. First of all, the length of the boundary must be equal. Then for classical one, for classical vertices, L is arbitrary. However, for quantum version, L must be smaller or equal to L star, the length of the boundary geodesic. It looks like there is a contradiction. We say that SR is larger than 2L star, but for quantum version here, L cannot be larger than L star. So how to relate them? It looks like there must be something subtle here. For this one, it looks okay because L is arbitrary here. So we can immediately have a restricted simple relation, which means classical string vertices. This one is equivalent to tripartite reflected surface SR. However, you see, I emphasize this is for classical, which means a classic one. And here is tree level, only tree level. We say once this one is not tree level, we have to use quantum version. Moreover, even for this one, there is still some restriction because these 3 SR could be different, but here L must be identical. So this relation looks a little bit arbitrary and carries not too much information. We want to go to, I do not left the two. How many minutes do I left?
Yeah, you have at least another 10 minutes, but you're welcome to run another 15 or
10 minutes. Okay, all right. Okay.
plenty of time.
Let me speed up. To obtain some more interesting relation, let us focus on the Perkinian critical length L star and 2L star in 2 theory. It turns out this is not a coincidence, but an important conclusion in hyperbolic geometry. From booster corollary 4.1.2, it's not hard to prove that corollary is 3. Considering two closed geodesic sigma and delta on some arbitrary hyperbolic surface here, it's on x pieces, x piece. If sigma and delta intersect twice, we will have this important result. Then one of them must be larger than 12 star, at least one of them. Now let us show how to realize this coronary in our case. We glue 2, 3 string vertices with 0, 3 along the blue geodesic here boundary sigma to construct an X piece. So this X piece is constructed by 2 Y pieces. This is one Y piece, this is another one. We glue them together. So here you look at sigma is the same as the boundary. If the boundary is smaller than L star, sigma must be larger than 2L star. So sigma serves so we have to say either sigma or delta must be larger than 2L star and the surface reflected surface for whatever length of the classical string vertices. This implies that the trace reflected surfaces can be constructed completely by classical string vertices, but only tree diagram. More interesting story occurs in quantum theory, where the length of the boundary of the string vertices is bounded by L not less than L star. In this case, there is a remark. We say that the blue line, the length of the blue geodesics are always not larger than L star, but this delta, of course, is larger than 2L star, which is precisely which can precisely serve as the reflected surface. And moreover, there is a remarkable quantitative relation between sigma and delta, which is this one. So we got a quantitative relation between the reflected entropy and the length of the string vertices. It's like this. Okay, this is just some numeric result. So there is from this relationship, we see that the minimum value of S reflected entropy from this one, which is this quantity. Of course, this quantity we say that it's larger than 2L star, precisely match the conclusion of reflected entropy. However, in the CFT, we only know that it's larger than this one. We cannot get this number, but here we got this number. So we have some extra. The string vertices method give us some more information here. We thus have this relation quantum string vertices V04 correspond to can be used to construct bipartite reflected surface SR. And moreover, I'm going to give more examples, but because of time, let me just go quickly. We'll give some examples. The first one is how to obtain the reflected surfaces of bipartite mixed state from the string vertices V04. From previous one, we said here, this is the reflected surface. This one is the we glue this. This is the Y pants. This is another Y pants. We glue the Y pants up down side, from up to down. So this curve is smaller than L star, but this curve is larger than 2L star and is reflected entropy. So when we glue two Y pants upside down, it's kind of subtle here. We say that when we so this is gluing two y times up and down to get a left and right entanglement entropy. This is left and right entangling when we go to y times up down side. This is another complicated, more complicated one. We just got the tripartite from this V04. Like this. In order to get this one from previous one, we just this one got this one, the generalized one to finally this one. So this one finally, because this all those parts disappears, only left with those three lines, which is this one. Okay. Of course, again, there are some quantitative relationship here, and there one might be puzzled that the apparent restriction that the length of the constructed reflected surface must be equal. The most explicit way to resolve this puzzle is to consider the construction of pentapartite mixed state. The bulk geometry can be built by 5x pieces, since the string vertices have the same length L here. We could say they have the same length L, but finally, when we got this one, there would be an extra another one appear. This one, the length of this one is different from those curves. So so this can perfectly solve this puzzle. And finally, let me say, there is a holographic visualization of the phase transition. At the beginning, we say that there is a phase transition of the entanglement, the reflected entanglement entropy. We have noted that there is a minimum value of SR, namely SR must be larger than this one. Below this bound, the entanglement wedge suddenly disappears in the safety side. From the corollary 3, either sigma or delta is larger than 2L star when the length of the boundary geodesy increases from L, small l to larger L. The left-right entanglement changes to up-down entanglement, which means, all right, if this one is larger than 2L star, we have the entanglement from left to right. But when this one becomes smaller, this one becomes larger. So it becomes entangling from upside to downside. This is nothing but a move in hyperbolic geometry. In other words, the phase transition in CFT between the disconnected phase to the connected phase is actually on a move of X piece in the dual geometry. All right, let me just say the summary and discussion. We propose how to construct reflected surfaces from string vertices. This relation builds a connection between entanglement and closed string field theory. We therefore conjecture that the hyperbolic string vertices play a fundamental role as the building blocks of spacetime. The quantum BV equation can be used to construct or restrict the safety dual because it's dynamic. Geometric master BV equation controls various interactions, such as taking boundary and showing together between vertices. Since vertices is determined, the vertices are determined by the entanglement entropies between mixed state of subsystems, there could be a boundary version for the geometric master equation, which tells us how two systems to entangle with each other, which means we generalize a bulk dynamic equation to a boundary. And then the close connection between the two theories is not really surprising. The reason is that both theory, the underlying reason is that both theories are rooted in hyperbolic geometry. So at first glance, it looks a little bit surprising, but when we consider that their underlying foundation of those theories, so that looks very natural. So, all right, this is my talk. Thank you for your for everyone. And all right.
Thanks so much, Haitang. That was really lovely. So yeah, if anybody has any questions, please go ahead and ask. We have plenty of time.
We are going to have the paper ready very soon. I think in a couple of days and upload. There are just some technical details left, and the draft is already should be done very soon.
So exciting.
We spent 2 years on this project.
Okay, if there aren't any questions at the moment, we can thank Haitang again. Thank you very much. That was a lovely talk.
Okay, thank you, everyone.